Hey guys, today we're going to start looking at waves in a little more detail than what we did the other day. Now that you know how waves look in terms of the equation and how to create them on Desmos, we want to make it more real in terms of real life. So just to remind you of where we've been, we saw that waves are a propagation of a disturbance through space and time. You start with a nice smooth surface for the water. We disturb it, and that disturbance travels outward. That's what we call a wave. It's a transfer of energy, not a transfer of matter. We saw we can make a wave on a string by just oscillating our hands up and down. This is our disturbance, and it travels through the rope. You saw it form the sine curve. I told you that waves transfer energy, not matter. So if you're out in the ocean and the wave goes by, you bob up and down. And we saw that at this point, it's not a wave anymore. It's a breaker. And then it actually can push matter forward. We saw again our equation. Notice it's y as a function of x and time. Notice how the particles move up and down, and you guys did this for yourself on Desmos to verify that this equation actually does produce wave-like motion. I'd like you guys to do a practice problem today where you're asked to find different things about the wave. The most important thing is when you get these pictures, look at the x-axis. If it's horizontal position down there, then what you have the distance from one part of the wave to another similar part is called the wavelength. It goes by this symbol, and it's measured in meters or centimeters. Meters is going to be the standard, but this one is measured in centimeters. Wavelength. You get it when it's horizontal position. If instead it's time, then that same process does not get you the wavelength, it gets you the period. Remember, you can be more accurate, so you don't mess up when you do this, by doing a large number of waves and then dividing. You'll get less error this way. So you count them off. I have 1 wave, 2 wave, 3, 4, 5, 6, 7 waves, and I started at around 1.9 seconds. And I ended at around 6.7 seconds. So again, to get the period, you do the total time divided by the number of waves. In this case, again, our time is 6.7 minus 1.9. We just arbitrarily started at the 1.9 and we ended at the 6.7. Count your waves again. Don't count where you start. That's 0. So it's 1, 2, 3, 4, 5, 6, 7. So you'd subtract your 2 times, get a time, divide by this, and you got the period. Again, the frequency is the opposite. That's number of waves over time. So that is the reciprocal of the period. So I'm going to ask you to do that just to make sure you know the difference between your waves. Again, you can find the amplitude from either one of these. Okay, now I'd like to talk to you guys about 2 new things today. The production of waves. How do you get a wave started? And then the second thing we want to talk about is the 2 main types of waves. Okay, so if it's a wave on a string, you start it with some sort of disturbance. In this case, we're going to whack the string with a ruler, a meter stick actually. That disturbance will then travel through the string. So you can see we whack the string. The disturbance does not stay localized, but it travels right down the string and then back again. So if you have a string, you just flick it, you move it, you pluck it if it's a guitar string. You move the bow across it if it's a violin. You have to do something to make the string start to move. And then that movement, that disturbance, travels through the string. Here's a picture that someone took. It's amazing. They put their camera inside their guitar so you can actually watch the wave travel through the strings of the guitar. And you can see these beautiful sine curves showing up every time it focuses properly. And again, it starts with the plucking of the string. Okay? And again, beautiful sine curves in our strings. Sound waves. How do you start a sound wave? Same thing. You need some sort of movement, some sort of oscillation, some sort of disturbance. So for instance, you might use a speaker. And that speaker will oscillate. And as it oscillates, there's no string involved, but there's air particles that it compresses and then spreads apart. Compresses and then spreads apart. So as we watch our speaker move, each time it moves, it sends out a sound wave. And we'll talk more detail about how that actually looks in a little bit. But the production is started by some sort of vibration. A vibrating vocal cord, a vibrating guitar string, a vibrating speaker. Sound waves need a physical object to be moving, oscillating, in order to produce sound. It could be a top of a drum. Okay, so we're going to whack the drum with our drumstick, and you'll see the drum head oscillates, pushes on the air above it, and creates a chain reaction, which we'll be looking at in a little bit again, to send the sound wave out into the air. Okay? Again, it starts with some kind of oscillation. The final one we want to talk about is light waves. Light waves, very specifically, the oscillation that makes a light wave has to be a charged object, a proton, an electron, some sort of charged object that's not just sitting still, but it's actually oscillating or accelerating. Right now I have a proton, and the lines that you see around it are the electric field lines. And when we oscillate the charge, you'll see how the electric field moves back and forth to follow the charge. And it's that moving electric field and magnetic field that we pick up as light. Okay, so light, we'll talk again in more detail about what light actually is, but it's started by an oscillating charge. Okay? So, now that we understand that all waves are started by a disturbance, it could be a physical disturbance, like our vocal cords vibrating for sound, or it could be a charge moving for light. We want to talk about what type of waves we might make. So there are two main types. They're called transverse waves and longitudinal waves, and this is what they look like. A transverse wave is our typical, looks like a sine curve wave. It is a wave in which the energy is moving one way and the oscillations are moving at a right angle to that. So the energy travel is going horizontally. The oscillations of our particles are going vertically. This is called transverse. So energy travels horizontally. Vibrations are at a right angle to that. That is known as transverse. Longitudinal is not the same thing. Longitudinal, our energy is once again traveling horizontally. But this time, the oscillations are also horizontal. They're parallel to the energy. So this time, vibrations are in the same direction as the energy. Okay? So longitudinal, transverse. You'll notice this is a longitudinal wave. This is not the greatest video. I was hoping to show you this in person, but this is a slinky suspended from a bar, and you can see the person as they move their hand back and forth. They compress the slinky, they pull the slinky back again. They compress it, they pull it back. Those compressions travel through the slinky. That is known as longitudinal. Here's transverse. You can see the particles are moving up and down, and the energy is traveling horizontally. Here again is longitudinal, so we create our pulse by compressing and moving the spring back and forth, and you can see that compression traveling through the slinky. The energy is traveling in the same direction as the vibrations. Longitudinal. Okay, so which is which? It turns out that sound waves are longitudinal. As the speaker moves back and forth, it compresses the air in front of it. Compresses it, stretches it. Compresses it, stretches it. What it actually does is it creates high pressure when it compresses and low pressure when it moves back again. And those compressions of high pressure travel through the air and they reach our ear, and we pick those up as sound waves. So sound waves are longitudinal. Compressions and then low pressure. High pressure, low pressure, sound waves. Kind of looks something like this. So here's our oscillating speaker. Compresses the air, spreads the air apart. Compresses the air, spreads the air apart. Those compressions travel. They propagate through space and time. The oscillations, again, are in the same direction the energy moves. If you were to look at this sound wave as a pressure wave, then our familiar sine curve reemerges. You can see the pressure goes from atmospheric pressure to a high pressure, back to atmospheric, and then to a pressure that is actually lower than atmospheric as the speaker moves backwards. So it's high pressure, low pressure, high pressure, low pressure, traveling through space and time. That is what a sound wave is. Okay? So you can see high pressure when it's compressed, low pressure when it's spread apart, high pressure when it's compressed again. The distance from high pressure to high pressure is called your wavelength. You could also measure it low pressure to low pressure and call it your wavelength. Here's a demo I would have shown for you if we were in school, but I have a video of it, luckily. So I have a glass tube, and inside the glass tube is just air, and I put a bunch of quark dust in there. And I have a speaker playing back here. And you can see the quark dust oscillating back and forth as the sound wave passes through it. And you would have your wavelength being the distance between the high and low pressure. In this case, the high pressures are right here. Okay, so that is sound. It is a longitudinal wave. You can see the energy traveling from the speaker, and you can see the oscillations are parallel to that. Finally, here's a light wave. Light waves, again, start from oscillating charges. A great example of this is in a radio tower where they are sending out a radio signal. They oscillate an electron up and down at a certain frequency. It sends out a wave through the electric field, and the oscillation electric field, you could see, is in one direction, and the energy is at a right angle to that. So light, transverse. Sound, longitudinal. All waves are started with oscillations. So anyway, best of luck. I will be putting some stuff online. Make sure you go through all that to show me that you understand what we did today. Have a great day.